In this section, we will go a bit deeper into the instrumentation topic, exploring different kinds of compiler targets and instrumentation options. Before continuing, let's make a quick recap. AFL is not just about randomly throwing inputs at the program, but we say that it uses something called coverage-based fuzzing. This means that AFL tracks which part of the code are executed when different inputs are tested. By doing this, we can map out which inputs trigger which part of the code, and aim to cover as much of the program as possible. The goal is to find errors not just in the most common or obvious code path, but through the entire code base. And to do this, we need also to build a collection of useful inputs, also known as corpus. This process starts with a few manually created seed inputs. Then, the seed inputs are mutated, meaning they are randomly altered, and the AFL checks if the changes cause new part of the code to execute. If a mutation leads to new code being covered, it's considered interesting and added to the corpus for further testing. Over time, with continuous mutation and testing, we develop a robust corpus that covers as much of the code base as possible, increasing our chance of finding bugs through the entire program. Okay, so now what we want to investigate is how AFL keeps track of what code paths are executed and how the coverage map is built. AFL currently supports many forms of coverage. The three most common are PCGuard, LTO, and GCC plugin, but the two most supported are PCGuard and LTO. In this section, we exclude the GCC plugin, and we start with PCGuard, that is also the coverage mode that we used in the previous exercises. PCGuard is a type of code coverage instrumentation mechanism implemented within LLVM. PCGuard operates inserting additional instructions during compilation phase that record the program's execution path in a way that allow it to gather feedback on the execution paths during fuzzing testing. It works by leveraging control flow integrity mechanisms, such as tracking direct jumps, function calls, and other complex code paths that might be hard to reach using traditional fuzzing techniques. You can imagine it by a tool that automatically adds some code in the source files while it's compiled, every time there is a change in the flow of the program. To visualize it, on the code snippet on the right, you can see that we added some code in red to track the two different branches of the if-else statement. Please note that because this feature relies on the internal of LLVM, it is CLang specific and will not work with GCC. On the other side, we have another instrumentation that is LTO, that stands for Link Time Optimization. From an high-level point of view, PCGuard and LTO are the same. What is changing is the way they use to keep track of the explored code at runtime. In particular, LTO instruments at link time when we have all the files precompiled, and to do that, we have to compile our software in LTO mode. To better explain it, let's have a quick look to the compiling process. We start with the preprocessing that prepares the source code for a compilation, expanding all the macros, like the find and the ifdef, incorporates the files in the included directive, and produce the preprocessed source file. The preprocessed code is then passed to the compiler that translates the human-readable C++ code into assembly language, performing syntax type checking and other high-level optimizations. The result is an assembly code that is platform-specific. The assembler takes the assembly language code and converts it into machine code, binary mode. This machine code is platform-dependent and forms an intermediate object file. The output is .object or .o file, depending on the system. Finally, the linker takes one or more object files generated by the assembler and combines them into a single executable. It resolves the references to functions and variables, ensuring that function calls and variables in different files or libraries point to the correct memory addresses. The linker might link to external libraries, for example, the standard libraries like libstdc, and the final result is that it's an executable file like an ELF file for Linux. Now, if we look to LTO, we can see that before the linking stage, we also generate an intermediate representation. In normal compilation, each source file is compiling into an object file, like we said, a .o or .object file on its own. But with LTO, instead of just generating machine code, the compiler also creates an intermediate representation of the code. In our case, the intermediate representation is LLVM intermediate representation, because of course we are using LLVM-based compilers. This intermediate representation is a low-level version of the program, but it's still independent of the target architecture and can be optimized even further. Then, during the linking stage in LTO mode, the linker doesn't just combine object files, It also performs extra optimization across the whole program. Essentially, the linker can see all the object files at once and optimize the entire program, such as by doing function inlining or removing unnecessary code. For AFL, we need the right compiler, which in this case it's AFL CLang LTO for C code and AFL CLang LTO++ for C++ code. These compilers handles the LTO options and use a special AFL linker instead of the regular system linker. The AFL LLVM linker gathers all the LTO files to link them and add the necessary instruments for code coverage. In short, we can say that the main differences between AFL CLang Fast and AFL CLang LTO is that the first instrument the target during compilation phase, while the second instrument the target during the linking phase. The result is that AFL CLang Fast has a faster compilation process, but lacks whole program optimizations, while on the other hand, AFL CLang LTO has a better overview of the entire code thanks to the intermediate representation that allows to implement better optimizations. In this slide, you can see a quick overview that can help you to choose the right option. Do you need fast compilation times? Your target is not so complex? Go for AFL CLang Fast. Do you want better fuzzing performance and your application is more complex? Go for AFL CLang LTO. A better flow decision is provided in the official AFL documentation under the fuzzing in depth section that explains you which instrumentation you should use. Like you can see in the picture, the first option is to use LTO mode. And then, if it is not possible, for example, if you don't have CLang version 11 or more, they suggest to you to use AFL CLang Fast. That is also compatible with older version of CLang. Finally, the last suggested option is to use GCC plugin.